Hi everyone. I just wanted to make a video um, to help with some of the confusion that I've seen around energy balances and some questions people had around homework 8. You totally don't have to watch this video, totally optional. This isn't a discussion section or a lecture, there's no participation points. So if you feel like you understand energy balances or you're just busy this week and don't want to hear me talk, you totally can stop watching this now. But a few people in my office hours and a few people who I talked to afterwards had asked if there was a way that we could clarify energy balances a little bit more. So this is sort of just a supplemental video to help you if you need that. So I'm going to start with the first problem from the homework, which is 3.59. I think this was probably the simplest problem on the homework. So I'm starting here as a way to illustrate some of the concepts because I think if you have trouble with this problem, you'll probably have trouble with some of the others. Okay, so there are a few different ways of approaching energy balance problems. And I'm going to try to illustrate a few different ways of coming at this problem. So the way that the book likes to do it is they like to draw every process as a more complicated process flow diagram. And the benefit of that is that it breaks everything down into steps. There are really well-defined streams that you can solve for. The downside is that you have to draw a whole new process flow diagram and it's complicated. So I personally, my instinct isn't to go that route. I'll show you my way second, but I'll start with the book way. So for this problem, what's happening is that we have water coming in as a gas. It's at 240 degrees C and leaving as a liquid at 70 degrees C. So that water is losing heat. And that heat is absorbed by this styrene that gets heated. So on page 200, there's a physical properties table. You can look up the melting point and boiling point of styrene. And from that, you can tell that the melting point is below 10 degrees C. So styrene is coming in as a liquid. And we actually don't know the phase of styrene leaving the system because we don't know its temperature. But the boiling point is about 130 degrees C. So, maybe we can start with the assumption that styrene will remain a liquid. And then if we end up getting a temperature that's higher than that boiling point, we can sort of reverse course. Okay, so the way the book likes to do this is to draw a PFD, like I said. And so what's going to happen is we're going to have this heater. And we'll have styrene at 10 degrees C and 1 kilogram per minute entering, and styrene leaving at, let's call it T out. Then we're going to have water entering at 240. And what's going to happen to that water is actually 3 separate things. First, it's going to go as a gas from 240 to its boiling point, which is 100. Then it's going to condense, and then it's going to go from 100 as a liquid to 70 degrees as a liquid. So there's going to be 3 sort of processes that water goes through. So first, there's going to be a cooler, and we're going to have H2O at 100 degrees C. So here it's a gas, here it's a gas. Then we're going to have a condenser. We're going to have H2O at 100 degrees C. I'm not going to write the flow rate again, it hasn't changed. And here it is a liquid. And then the last thing is another cooler where we're going to have H2O at 70 degrees C as a liquid. And so now we've drawn sort of our flows of mass, and we can draw our transfers of heat. So I'm actually going to draw these in different colors. So in all three situations, our H2O is losing heat. So in our cooler, our H2O is losing heat, and that heat is going into styrene. I'm going to call this QA, for lack of a better term. And then in our second stream, our condenser, our H2O is also losing heat. I'm going to call that QB. And in our third process, if you want to call it that, our H2O is again losing heat. Let's call that QC. One thing that confuses folks is which direction QB should be going. And the way that I think of it is that the reason that we sweat is that water on our skin will evaporate and the water will absorb heat. So water absorbs heat when it vaporizes and loses heat when it condenses. And so our water here is condensing, so it's losing heat. Okay, so our delta Q of styrene is going to be the final state of styrene minus the initial state. So delta always means final minus initial. And that will equal QA plus QB plus QC. And we don't really have to think about what the signs of QA, QB, and QC are, because we kind of already thought about that when we were drawing which way our arrows are going. So QA is how much heat does water lose just by cooling as a gas from 240 to 100. So this is where you do have to think about signs a little bit. So our delta Q of water in this situation is going to be negative. There's going to be an 100 minus 240 in there. But then that's how much heat, that's the change in heat of the water. So the amount of heat that leaves the water is going to need to be a positive number. Don't know where that line came from. Okay, so QA should be a positive number. It is how much heat the water is losing. So you can think of QA as negative delta Q water upon cooling. And so that is going to be the mass flow rate, so 0.066 kilograms per minute, times the heat capacity, which is 1.94 kilojoules per kilogram degrees C, times 240 minus 100, or times sort of the negative of 100 minus 240. QB is how much heat water loses upon condensation. So that will be the heat of vaporization, so 2280 kilojoules per kilogram. And again, if you ever get confused about the sign, you know that the water should be losing heat upon condensation. So this QB, how much heat is lost, should be positive. And then QC is pretty analogous to QA. So we're going to do 0.066. And now we need the heat capacity of liquid water. So that's 4.17 kilojoules per kilogram degrees C times 100 minus 70. So if we combine all that together, Q styrene is the flow rate of styrene. So that is, well, let's first just say QA plus QB plus QC is delta Q styrene equals, if we plug all these numbers into our calculator, we're going to get 176.7 kilojoules per minute. And then what is delta Q styrene? Well, it's MCP delta T of styrene. So that equals our flow rate of styrene is 1 kilogram per minute. Our heat capacity of styrene is 1.76 kilojoules per kilogram degrees C. And then our delta T is T2 minus 10 degrees C. And then we can solve for T2, that's our only unknown here, and we get T2, where, sorry, T2 is our sort of outlet temperature. That equals 110 degrees C. And we can revisit that assumption that we made, which was that the styrene will still be a liquid. So our boiling point of styrene is 134, I believe. So 110 is below that, so our styrene is still a liquid, and we can feel good about that assumption that we made. One thing I forgot to mention is the book gives you these heat capacities in kilojoules per mole, and I just used the molar mass to convert that heat capacity into kilograms. I could just as easily have converted these flow rates into moles, so whichever of those is easiest for you. Okay, so like I mentioned, this method totally works, and if this makes sense to you and is how you want to solve it, then be my guest. I personally find this a little bit confusing. I find the signs confusing of should QA be positive or negative? How should I deal with that? And I just don't like doing the extra work of drawing an extra process flow diagram every time. So the way I like to do it is, to me, a little more intuitive. And I just sort of look at this process flow diagram and I say the heat energy in equals energy out. And the energy enters in streams 1 and streams 3. So those are the two streams entering our system. So I'm going to have Q1 plus Q3. And it leaves in streams 2 and streams 4. And then we can move the streams that are the same substance to the same side. So we want Q1 and Q2 on the same side as each other because they're both styrene, and Q3 and Q4 on the same side. So we can do Q2 minus Q1 equals Q3 minus Q4. So that is just rearranging which things are on which side. So like I said earlier, delta Q is always final minus initial. So delta Q styrene is Q2 minus Q1, and delta Q water is Q4 minus Q3. So if I look at this equation, that's the same as saying Q styrene equals negative, delta Q styrene equals negative delta Q water. So we can find our delta Q water in sort of a very similar logic of how we found QA, QB, and QC over here. So our water needs to cool condense, and cool again. But now, instead of looking at how much heat is lost, we're just very simply looking at the delta Q of the water. So delta Q water equals 0.066 kilograms per minute times this whole big quantity, which is the first thing that happens is that it needs to cool. So 1.94 kilojoules per kilogram degrees C. And it's cooling from 240 to 100, which is its boiling point. So the final temperature is 100 and the initial temperature is 240. And then it needs to condense, which means that it's losing energy. The heat of condensation is negative 2280 kilojoules per kilogram. And then it needs to cool again as a liquid. So we're going to do 4.17 kilojoules per kilogram degrees C times the final temperature, which is 70, minus the initial temperature, which is 100. And then all three of these terms are going to be negative because 100 minus 240 is negative. Obviously, negative 2280 is negative, and 70 minus 100 is negative. And I'm going to get delta Q water is negative 176.7 kilojoules per minute. And I know from up here that delta Q styrene equals negative delta Q water. And so that equals negative of negative 176.7. And so that equals 176.7. And then now we are right here, and the rest of our work will be the same. So that 176.7 equals 1 kilogram per minute times 1.76 kilojoules per kilogram degrees C times our final temperature, which is T2 or T out or whatever you want to call it, minus 10 degrees C. And we can solve and get T2 equals 110. So this is just a little more intuitive to me because I've just got a delta Q of water, and it's easy for me to think about what those signs should be. If you wanted to, you don't even have to explicitly write out these steps. You can just sort of say that I know that my energy change of styrene is how much energy my water is losing, and just jump straight here if you wanted to. So those are two equivalent but maybe conceptually different ways of thinking about this problem. Like I said, I prefer the green one. The green one makes more sense to me. If you prefer the purple and multicolored one because it makes more sense to you, then awesome. As long as you have a way that works for you, then you are good to go. Okay. I also wanted to run through the problem 3.71, which is the problem with the urns. So one thing that was confusing to some people on this is we are at steady state. So these earthenware pitchers are used to chill water. It's sort of describing this process generally here. So the temperature was initially the same as the air, and after a few hours, the water was cooler. So that is a non-steady state process. That is the process of the water cooling. But that's not the process we're analyzing. We're analyzing later on, the water is already cold, and we just need to balance the heat of conduction in with the heat that water is absorbing by evaporating. And so that is what it says here. Assume the water has been in this pitcher for a long time and its temperature is constant. So you don't need to worry about the temperature of the water in the pitcher changing because that temperature isn't changing. So if you wanted to try to draw a process flow diagram of this, probably what you would do is you would have this large urn of water. You would have 0.06 kilograms per hour of water at T water, which we're going to solve for. And then what happens to that water is it's at T water and it needs to evaporate at 39C. So we first need to heat it from T water to water at 39 degrees C. And then we need to evaporate it. And we end up with water vapor at 39 degrees C. And then if we draw our energy flows, there's this Q conduction coming into the urn, and then the heat to heat the water and to evaporate it is coming from the urn. And so we might have a QA and a QB. So Q conduction, we know. It is this equation that's given to us. And then we can find QA and QB pretty easily. So we know that Q conduction equals QA plus QB, and Q conduction equals U, which is 6.0 times 10 to the third joules per hour times Kelvin, times T outside minus T water. T outside is 39 degrees C, and T water is what we're solving for. One thing to be a bit careful of is joules versus kilojoules. So you might want to just deal with that now and say that instead of 6.0 times 10 to the 3 joules, we're going to say 6 kilojoules per hour times Kelvin. One question I got a lot is, well, this is in units of Kelvin and this is in units of Celsius. That seems bad. But what you have to remember is that the conversion from Celsius to Kelvin is just by adding some factor of 273. So the difference between two temperatures in Celsius is going to be the same as the difference between those two temperatures in Kelvin. So if you wanted to convert these temperatures to Kelvin, you can, but you do not have to. Okay, so here's where, to me, the signs get confusing. So QA is how much heat does it take to change the water from TW to 39 degrees C. So that's going to be our flow rate of water, which is just the flow rate of the small amount that's evaporating. So that's 0.06 kilograms per hour times the heat capacity of liquid water, which is 4.17 kilojoules per kilogram degrees C, times 39 minus T water. And then QB will be how much heat does it take to evaporate water? And so that will be also 0.06 kilograms per hour times 2280 kilojoules per kilogram. So to me, those signs are a little confusing, and I have to go back and think, well, I want QA to be positive. This water needs to absorb heat. How much heat is it absorbing? It should be a positive number, and that lets me go back and check my signs. And when we do that, now we have an equation where our only unknown is T water. It's in there twice, and we can solve for T water equals 15 degrees C. So, like I said, I don't really like to draw that process flow diagram. I personally jumped straight here just by thinking, I know I need the conduction to be balanced by heat being absorbed by the water. Um, how can I make that happen? Well, how much heat is being absorbed by the water? But as always, if you prefer to draw that process flow diagram, if drawing that helps you visualize the flows of heat and get the signs right, that is totally fine. Okay, so that's all I have. I hope this was helpful. If you have any questions, please don't hesitate to ask on Piazza or email me. Again, this is not a discussion section. It's not a lecture. You don't have to turn anything in or get participation points. The goal of this was just to be helpful to you. So, yep, please let me know if you have any questions, and I will see you guys next week.